Hello, this is a follow-up. This is part two of Peter Ponder's sliding mode control. And again, I'm starting with the same parameters, except for now I have a second order system. This basically approximates a hydraulic system uh, in velocity control, and then this integrates velocity into position. So what I have here is an underdamped system that represents kind of like a mess between two springs, which is the hydraulic volume on either side. So I have a gain. I'm using the same gain as before, but I have to use a separate natural frequency and a damping factor. This damping factor is very, very low compared to what most hydraulic systems happen to be, but I have a system that I can test on where the damping factor is actually 0.06. So I need to be able to test on very, very low damping factors that would oscillate kind of like a slinky. And if you can control a slinky, you've got it made. Again, this is to vary the parameters just to show the robustness of the sliding mode control, even with the second order system here. This next part is the state space with in Laplace or continuous mode, and then I convert it to digital format down here. Um, Something I didn't mention in the previous video is that MATLAB will do this for you automatically, but MathCAD does not have that capability, so I'm just showing the math that's involved in converting from the continuous time to the discrete time. So now I have the same valves as before. I got the nonlinear valve. And now instead of having just a position of velocity, I got a position, velocity, and acceleration. And I've got this lambda, which is my response. Again, the two things you have to adjust is the response and this boundary layer or switching layer, and this maximum output, which is always 100%. So 1 is 100%. So now I'm using the hyperbolic tangent version, and I've got the weighting. Now I got this is a R is the target position, velocity, and acceleration. X is the actual position, velocity, and acceleration. And these are the weightings, and these weightings are based on a well, they're time constants, but basically it's like having the time 1 plus the time constant squared. So, or S times the time constant plus 1 squared. This is the output. Um, anyway, this will ensure that I don't have overshoot. This is the output. This is the state space calculation with the nonlinear valve calculation, and then this is the control output. Okay, these are my step jumps. They're identical to what I had before, and you can see that it's moving into position without overshooting, and you can see that the amount of time that it takes to get into position where it comes out of saturation and starts decelerating is actually much less than what I had in the previous example, and that's because I've got the frequency, the lambda value, much higher. If I reduce the lambda value, let's just come up here and see if I can reduce this a little bit. Let's reduce it to a 1. Oops, 1. Okay, now, well, now it's switching all the time. But basically what it's doing is it's coming out of saturation much earlier. And again, it's switching all the time. Let me make this delta a little bit smaller so that we don't have to see it switching all the time. And now you can see that it's much, much more gentle in how it approaches the set point. So those are the two parameters that you need to adjust, and it's pretty easy to adjust them to get a desired response. Now I need to explain something here. Because I've got a second order system that's totally, well, it's underdamped. And when the output goes into saturation, you're basically running an open loop mode and you're not really controlling the oscillations. So what happens is that I'm seeing oscillations here where if I were to plot the velocity above 1 meter per second, you would see it actually go above 1 meter per second. But then you can see as it approaches my set point that it ramps down nicely without overshooting. And that's because of these parameters that I chose right here. Now, going down a little bit, let's try a motion profile. And you can see that the target and actual position track fairly accurately. If I want to, you can see that the sliding or the root mean squared error is almost 4 millimeters in error. And the reason why that is because up here I just changed the that response value from 5 to 1. Let's move that back to 5. And we can go down here. And now this is less. And if I make the that switching area smaller, make that back to what it was originally, 1,000ths. That's the same as what it was on the first example. Now, using the same parameters I had before, the error is, root mean squared error is less than 4 millimeters during the motion profile. And here you can see the error in position, and it's less than 10 to the minus 3, which means it's less than a millimeter. And then the actual, or the velocity error is less than 3 millimeters per second. So you can see that this is, again, is very robust. So just for playing around, let's try one of these other valves, and let's disable this one. Now we've got the this is the cubic curvilinear. Well, a lot of valves will call this curvilinear, but it's not linear at all. Again, this works just about the same. And this is about the same. The error is less than half a millimeter. So what I want to get across is, again, the sliding mode control can be implemented in hardware, and it can be very robust. If you take a look at or look up implementing the hyperbolic tangent using hardware or analog circuitry, you can find a circuit that will do this. It might not be perfect, but it'll be very robust, and it should be able to, well, hopefully it will meet your requirements. So again, this is the plant that I'm using, the gains, and then I'm changing the parameters. Oh, let's change the parameters a little bit so you can see how that works. Let's go on down. So this is the original parameters, and this is after they're modified. And oops. Well, let's just do a Control F9. That changes the simulation. And you can see the root mean square doesn't change by much. So even if your plant varies, this will still control your system very, very well. And if it just must work and you can't rely on computers, this is the way to go. So give me a like, and hopefully you learned something from this example. Bye.